So in the last video, I left off talking about electroplating, and I'm just going to continue where I left off. So if you didn't watch the last video, make sure you watch it before you watch this video. So again, electrons are leaving from the silver bar, so this is being oxidized, and it is going over to the spoon, and now the spoon has a negative charge. And because of that, it is going to attract the positive silver ions onto it. And the silver ions, once they take the electron, are going to form silver solid. So the silver is being reduced from a positive ion, it's gaining an electron. Again, this should be an arrow going to silver solid. So reduction is happening here. So this is our cathode. Remember red cat, anox. And our cathode, because again this is an electrolytic cell, has a negative charge because it now has the electrons. And on the other side, our silver solid is being oxidized to form silver ions that have lost an electron. So on this side, we have our oxidation, so this is the anode. And again, this is an electrolytic cell, so the anode is now positive. Okay, so the last bullet point of how electrolytic cells, what they can do is, let's go all the way back to our first slide, is electrolysis can also be used to split water. So we are going to look at what that cell looks like right now. So here's what the cell looks like. You essentially have the hydrogen gas being attracted to one electrode. Hydrogen is attracted to one electrode, making hydrogen gas, and the oxygen is attracted to the other electrode where you're going to make oxygen gas. And we still have the cathode is where reduction is happening, red cat, and ox, at the anode, oxidation is happening. And all electrolytic cells, your anode is positive and your cathode is negative. The half reactions for these cells are a little bit more complicated looking. This is the oxidation half reaction. Again, this is an arrow. So on at the anode, you have water, which is now breaking in to form oxygen and hydrogen ions. And because overall you're releasing 4 electrons here, this is your oxidation half reaction because you are producing these electrons. It's on the product side. Your half reaction for the reduction side at the cathode is you have your water that's gaining those 4 electrons, forming hydrogen gas and hydroxide ions. And then you can add these two half reactions together because there's 4 electrons being produced and 4 electrons entering into the reaction. And you get your 2 water molecules, arrow, oxygen gas, and hydrogen gas. I won't expect you to be able to rate the half reactions for electrolysis of water, but this is what it looks like. So we have now finished talking about the 3 different types of electrolytic cells and the 1 main type of voltaic cell, which are both categorized as electrochemical cells. So again, to go back to the slide that talks about the differences between the cells, the key thing that you really need to know is that, I went too far, is that unlike voltaic cells, electrolytic cells are not spontaneous. All of the electrolytic cells we looked at, there's a battery. You have a battery required here to make this happen. You have a battery required in the next one to make this one happen. And you have a battery required in this one, to make this one happen, they all require batteries, which is unlike the voltaic cell. There's no battery in the voltaic cell. There's just a voltmeter. Here, see, no battery, just voltmeter. And then the other key difference is that the charges are switched with electrolytic cells. The anode is positive and the cathode is negative, which is different from the voltaic cell, where your anode was negative and the cathode was positive. Okay? And that is everything new that we have learned. Okay, so we're going to work on this worksheet together. This is the electrochemical cell worksheet that is posted on level 4. You do not have to upload it because we're going to do it together. Sorry, I'm like moving the page. We're going to do it together, and I'm just going to put questions on the Edpuzzle video, as you will see in just a second, that will make you answer the question before I answer the question for you. Okay, so here it says electrochemical cell. Remember, that's the overall category of all cells. Is it, however, a voltaic cell, or is it electrolytic cell? Okay. It is a voltaic cell, and we know that because there is a big V here, meaning that there's a voltmeter reading the power coming off of the battery. There's no battery written anywhere on the cell telling you that there's nothing supplying the power. It is just naturally coming from the cell itself. So we have chemical energy in this cell that's being converted into electrical energy. Okay, answer the questions below referring to the above diagram and the table of standard electrode potentials. Which is more easily oxidized, metal, aluminum, or lead? So is aluminum oxidized more easily or lead oxidized more easily? And again, you need to look at your reference table for this one. So it looks like aluminum is here, and lead is down here. So aluminum is oxidized more easily, and lead will be reduced. So aluminum, so we're going to write aluminum right here, and it is the neutral aluminum that will be oxidized. What is the balanced equation showing the spontaneous reaction that occurs? Well, in order to answer that, we really have to write the half reactions and then add the half reactions together. So, because we know aluminum is oxidized, I know that the half reaction will look like Al goes to Al plus 3. I know it has a positive 3 charge because this 3 crisscrosses to go up, and there's a 1 there. So aluminum has a plus 3 charge, and so it is losing 3 electrons. So that is the oxidation half reaction. And I know that the reduction half reaction, we will have lead ion. Lead here will have a 2+ charge, crisscross rule. So here we have lead Pb 2+ plus 2 electrons is going to get us lead neutral. The only way to add these two half reactions together is if you have the same number of electrons being added as what's being released. So I need to multiply the top reaction by 2. So that way we can have 6 electrons because that is our least common multiple. And here the reduction reaction I'm going to multiply by 3. Thank you. So overall, when you add this together, you will have 2 aluminum. Again, this 2 multiplies onto all of the species in the reaction. So we have 2 aluminum neutral Everything on the left side of the arrow is added together, and our electrons, because you'll have 6 electrons here and 6 electrons there, they cancel. So also left of the arrow we have our 3pb2+, and then on the right side of the arrow we have our Al. Well, we have 2 of them because the 2 multiplied onto it. Al plus 3 plus 3pb neutral. Thank you. Okay, so this is our overall reaction. I did not include the spectator ions, which are nitrate. So that would make this reaction look a little bit different with nitrate ions attached to the lead here and the aluminum here, but I'm not going to worry about them for now. What is the maximum voltage that the above cell can produce? So if you remember from my last video, we found the electrochemical reduction potentials and we added them together. So here are our reduction potentials. We have, again, we're looking at lead and aluminum. Lead is being reduced, so this is the way that the lead half reaction looks. So we're gonna just keep negative 0.13 as it is. Aluminum, however, is not being reduced, it's being oxidized. So we have to flip this half reaction, and so we also flip the charge of the reduction potential energy. So this will be a positive 1.66 added to a negative 0.13, and so that gets you 1.53. So our answer for 3 is positive 1.53. Sorry, that's a positive 1.53. What is the direction of electron flow in the wire? So again, who is being oxidized here? Aluminum is the half reaction that's being oxidized. So electrons are flowing from aluminum to lead. So here electrons are going that way, so they're going to the right. So the direction of flow is to the right. What is the direction of positive ion flow in the salt bridge? So here is our salt bridge, is right in the middle. So we are going to have, because there's salt in our salt bridge, we're going to have a positive ion in here, and we're going to have a negative ion in here. And to understand where they're going, we have to look at each half cell. So we know aluminum is losing electrons, and when it loses electrons, it is going to form more positive aluminum ions in solution. And to balance the charge of these positive ions, we are going to need the negative ion to come out of the salt bridge to continue making the solution neutral. So that means that we know that the positive ion is going to have to go out that direction. And that also makes sense because here in solution we have lead ions. I know that we have lead ions because we have the salt, lead nitrate, that is making lead ions. And lead ions are forming solid lead on this electrode. So we're using the positive ions, so we have to replenish the positive ions from the salt bridge into the solution so that we again maintain the same charge. So positive ions also flow to the right. Which electrode is decreasing in size? Well, again, aluminum is turning from pure aluminum into aluminum ions. So this is the guy that's getting smaller. And here we have lead ions that are going and forming lead solid. So the lead side is getting bigger. What is happening to the concentration of aluminum ions? It's increasing as the reaction's going on, as we just said. And the lead ions are being used to form lead solid, so that is decreasing. What is the voltage in this cell when it reaches equilibrium? It's going to be 0.